Continuing with Born-Haber cycles then, we'll start off by looking at this example. As you can see, it's incomplete at the moment. It's a Born-Haber cycle for magnesium oxide. So following that same formula, solid ionic lattice at the bottom, near the top, gaseous ions. Magnesium oxide is composed of 2 plus and 2 minus ions when you think about the formulae and the electronic structures of those ions and the atoms that they come from. As always as well, we've got enthalpy of formation here. So from the elements, remember that O2, as we well know, is the element for oxygen. And so to get one O atom into 1 mole of MgO formed from its elements, you balance that with half an O2. Notice again the arrow up here, this is lattice dissociation, the arrow is pointing upwards, breaking apart this solid lattice. Same value, opposite sign if it was pointing downwards, that would be lattice formation. To save time, basically, I've filled in most of what we need to do. There's something missing, which is really one of our big talking points for this video. So when you look at the steps, you've got here solid magnesium to gaseous magnesium. So that's going to be atomization of Mg. Second step, now hopefully you know what I'm about to say about this diatomic non-metal. 2 possible definitions there, aren't there? That is OO, double bond, because O2 contains a double bond, breaking to form 1 mole of O. So what we've got is half a mole of OO double bonds. So not an Avogadro, but half an Avogadro's worth. That much energy invested to break that many OO double bonds to form 1 mole of gaseous O atoms. So one option is that is half the enthalpy of bond dissociation of the oxygen double bond that holds O2 together. But that's kilojoules per mole of bonds broken, and we've only got half that quantity, so we'd halve the value. Again, hopefully you already knew this. Alternatively, we'd say that it is the enthalpy of atomization of the element oxygen. You can write O or O2 there. Enthalpy change from 1 mole of gaseous atoms is formed from the element in its standard state. So that's covered. Then we've got our ionizations, our first ionization energy of magnesium. And then after that, the second ionization energy of magnesium. So far, so familiar compared to the magnesium fluoride example we had before. This is one of the things we're going to talk about in this next video then, electron affinity. So the first electron affinity is always exothermic, which means arrow points down. We'll think about why in a moment. However, I'll tell you this now, the second and any subsequent, if there was a third, for example, electron affinities are endothermic. So let's just take that at face value for now. Typical that I haven't left myself enough space. This is awkward, but again, there's something we can say about getting around this. I'm going to have to sort of squeeze another energy level in there, because knowing what I know that it's going to be an exothermic change. Again, remember not to scale. Those lines being on the same line doesn't mean anything here. There's no grid for us to plot on. So that's the first electron affinity. I'm going to call it the 1EA. That's the process where one gaseous, it'll be a non-metal atom, O in this case, accepts one of the electrons that was released by the metal when it was ionized to form a single negatively charged ion. In the previous video, magnesium fluoride, that's as far as we had to go. That's exothermic. Again, we'll talk about why in a sec. The second, and if there was also a third electron affinity, involves 2 negatively charged particles, hint hint, coming together. That's endothermic. There's some kind of force that needs to be overcome there for that to be endothermic when we're talking about changes like these. So that means an arrow is going to be pointing upwards, back up to the gaseous ions. By the time we've done those 2 electron affinities, we've made it from gaseous O and 2 electrons to O 2 minus, also still gaseous. So again, I've really set myself a challenge here, trying to squeeze what I need to write into this space. This is magnesium 2, 1 electron and O minus. So I'm going to have to write quite small, but you get the idea is the important thing. Well, hopefully you get the idea. There we are. Now, that works just fine, and technically that's, well, even though we're not drawing it to scale, that's as accurate as we can get. We're going down for our endothermics and back up for our exothermics. Remember we said before, enthalpy of formation, it is normally exothermic, so it makes sense to write it going down all the time. Sometimes you might end up with a positive value to put in there. So be it if so. Now, a couple of things to say. We haven't yet got on to putting any numbers into an enthalpy formation, a broad energy cycle. An alternative, so I'm actually going to scribble some of this out now, nothing's wrong on that page though. An alternative way of showing those two electron affinity steps would be, very simply and easier to manage, just to write them both as downward arrows. There's nothing wrong with that, even though strictly speaking, since that second electron affinity, if I just write 2Ea, because obviously I'm a bit squeezed for space, and 1Ea to make O minus, magnesium 2 and an electron. Never forget your state symbols. Even though technically speaking that second electron affinity will be positive, it definitely will be endothermic, and so that arrow should be pointing up. We can be a bit flexible about it, a bit like we're flexible about delta HF, may sometimes be positive. As long as you navigate your cycle correctly, when we get onto the numbers you'll see that, then you're going to use these numbers correctly. So if we were going from here, around our energy cycle, just like we did in the Hess cycle, to here, and we're going to go with those arrows, so we'd add those values, which would mean adding a negative, then adding a positive. It doesn't really matter if the down arrow is pointing up or vice versa, provided you've got the correct number associated with each arrow. Now, let's move on then, second part of this video. Why is it that atomizations, ionizations, why is it that everything that we normally file on the left-hand side here, why are they always endothermic? Why is the first EA exo, but the second and third EAs endo? Why is lattice dissociation always endo and the other one exo? We're not going to talk about formation because we've said it lots of times, it can vary a bit. Well, it's pretty simple. So let's just talk about the sign on delta H in a Born-Haber cycle. We're not going to mention enthalpy of formation anymore. We've said enough about that. So enthalpy of atomization, enthalpy of bond dissociation, enthalpy of first ionization, second ionization, sorry, I'm just going to say IE, first, second, third, however many there are, it won't be more than 3. Those are always endothermic, so the sign on delta H is always positive. Your job is to be able to explain why. I'm not going to write notes on the page, you just need to listen and put notes in as you see fit. Well, in each case here, there are others which are always positive as well. We're always overcoming some kind of attractive force, so we have to do work against something, and that something is an electrostatic attraction. So in atomization, let's take the example up here. We've got solid magnesium, or solid any metal, turning into gaseous, that metal. So we're putting energy in order to overcome the electrostatic attraction between the positive metal ions in the metallic lattice and the delocalized electrons. In other words, we're breaking bonds, they'd be metallic bonds. So atomization is breaking bonds, basically. Magnesium solid to magnesium gas, energy in to separate the particles in the magnesium lattice, breaking the metallic bonds. We could be talking about the atomization of a non-metal, probably a diatomic non-metal would be typical for these sorts of examples we get given in this topic. Now we're also talking about bond dissociation at this point. Atomization here, it's also breaking bonds, breaking metallic bonds, or here breaking covalent bonds. And of course we can say the same about bond dissociation because we've already recognised this sort of factor of 2 relationship here. Do we balance it for 1 mole of gaseous atoms because it's atomization, or do we balance it for 1 mole of covalent bonds, which is double atomization, which is bond dissociation? So we're overcoming electrostatic forces of attraction. We know that a covalent bond isn't an ionic bond, nor a metallic, it's a covalent bond, but there is still an electrostatic force of attraction. You've got 2 positive nuclei, and that shared electron density, which is all around and in between, so they're both attracted to that common central point, you could argue. Ionization energy, we talked about that when we looked at electronic structure, and we looked for some evidence for our sublevel theory. Ionization energy always put in to overcome the electrostatic attraction between the nucleus and the electron which is being removed. So that also is an attraction to be overcome, energy has to be invested, so those are always endothermic processes. Let's just say a similar thing, there's no need to write notes on the paper for you here. Lattice dissociation, oh look, it's also breaking bonds. Here we've got magnesium 2+ ions, electrostatically attracted to oxide ions in a lattice, surrounded by oxides, surrounded by magnesiums, and on they go. And again, energy in to overcome those electrostatic forces of attraction between oppositely charged ions. And finally, no, actually we'll do electron affinity separately. Now, lattice formation then takes us into a bit of a helpful thought when we get onto electron affinity. Lattice formation is the complete opposite of overcoming an attraction. Here we've got gaseous ions, well, being allowed to attract rather than having energy put in to separate them. So it's the total opposite of breaking bonds, it's forming bonds. Bond forming is exothermic, we said. When these particles are allowed to interact and attract and stay attracted to each other and form a lattice structure with many others that are also nearby, they have a stabilising effect on each other, which means exothermic, basically chemical potential energy drops. The excess energy is released as heat to the surroundings, so exothermic. Now, any attraction being allowed to happen when we're talking chemicals like this will be an exothermic process. Bond forming is exothermic, ionic bond forming is also therefore exothermic, and as we'll see in a second, electron affinity, the first is also exothermic because there's some kind of attraction taking place rather than being broken. So the first electron affinity, let's take oxygen as our example. It's the formation of O- from a gaseous O atom and an electron. Since it's exothermic, in this context, that means there's an attraction taking place. I just want to remind you, combustion is exothermic. That's nothing to do with attractions. That's to do with more energy being released by bond forming than is taken in by bond breaking. But these are very specific little changes where there's a one-to-one attractive particle sort of interaction, like something plus something or something being removed. What's the attraction between here? I wonder if you can pick it up. It's something because it's exothermic. Well, it's the attraction between the nucleus in the atom that's about to receive that electron and the electron itself, the incoming electron. That's what the attraction is between, and it's exothermic with facilitating that. That's one way of thinking about it anyway. It works for what we're doing. The second electron affinity, and if there was a third, if we're making like a P3- or an N3- ion, group 5 negative ion of some sort, then think about this. Why would it be that when these two particles come together, that rather than there being an attraction, there's some kind of force that needs to be worked against. There's some kind of force that needs to be overcome to achieve the second electron affinities, process, which is make an oxide ion. Well, if you want more time to think, you better pause the video. It's a repulsive force here. So there's repulsion between these negatively charged particles. Yes, there is also the attraction because there's a nucleus in there somewhere and this electron's been drawn towards it and it will get contained in the outer shell of this oxide ion and it will stabilise it, full outer shell we say. But nonetheless, there's this like charge repulsion between the incoming electron and the negative particle. And there is a nucleus buried in there somewhere, but overall this particle, this O- ion, has a negative charge, and so there will be repulsion. So we have to overcome the repulsive force in order to get that electron in. And I say we have to, we're not actually doing anything here. When magnesium and oxygen react, the overall reaction is strongly exothermic. Delta HF is very negative, but this is one of the processes which does take place there. So there's another way of thinking about this, like how this is another illustration of how Born-Haber cycles are useful. Magnesium oxide reacts, it's massively exothermic. Magnesium plus oxygen reacts, it's massively exothermic. This is a large negative value down here. We can weigh up, so we could actually calculate delta HF if we've got an idea of these sorts of values. We can weigh up the various factors, steps in the process that must happen. So if we imagine magnesium and oxygen reacting to make magnesium oxide, we'd have to consider for a start the magnesium being obliterated, turning to gaseous atoms. Now when we burn magnesium, it does get very hot. It doesn't necessarily boil or sublime the magnesium, but the idea is that the magnesium lattice has to be broken. Also the oxygen-oxygen bonds have to be broken, and also the metal has to be ionized. Now delocalization is already a thing in magnesium, but every Mg present has to formally lose 2 electrons to the oxygens. The oxygens have to accept those electrons, and you see that there's an exo and then an endothermic component to that. And ultimately, once these ions have been formed, they will then attract. So the enthalpy of formation for an ionic substance depends on how much energy is taken in, how difficult is it to pull apart the metallic lattice, how difficult is it to pull apart the the covalent substance, how easy are the electrons transferred, that's released and then taken in, how far do we have to go up before we go back down again, and then ultimately, once we've got ions, how exothermic, i.e. how strong is the ionic bonding, is that lattice formation. So we've got the big ups, all the endothermic processes, and then we've got all the downs, and the question is where is there more? So we're not talking about bond forming and bond breaking anymore completely. It's not just that, but it's a similar thing. Enthalpy of formation, stable compounds basically have quite exothermic enthalpies of formation normally, and that would be because more energy is released in the exothermic processes that are described in a Born-Haber cycle than is taken in by those other endothermic processes that must happen, pulling apart the reactants, ionizing them in this case. That's offset by the attraction between the outcome, the ions. Okay, so that's it in a nutshell. Second electron affinity is negative. The third would be the same. I've never seen an example in an exam question, but we can think one through. So if you had a nitride ion, which is N3 minus, being formed from, well, originally it's elements, and you've gone through the whole process of the Born-Haber cycle, and you're up to the third electron affinity, it would make sense that that's going to be repulsive, and that's even going to be even more endothermic because there's a stronger repulsion there because you've got a 2- charge. So there you go. So that's all there was to say in this instalment. The third and final video for lesson 2, as it's become, is doing a calculation on a Born-Haber cycle, and let's get on to that one as soon as you're finished with this.